guys, how are you doing? So, let us recall our previous discussion, and who will tell me the difference between the potential energy and electrostatic potential. Our topic was electrostatic potential, and we initially considered potential energy of the system, electric field charge, and then we went from potential energy of this system to a feature of the electric field itself, which is called electrostatic potential. So what is the difference between them? So if we are talking about a system, electric field charge, then obviously potential energy is a property of this system. So we cannot introduce concept of potential energy when we have only electric field or only charge isolated from each other. So they need to be parts, like building blocks of the system. However, when we divide potential energy for given configuration of electric charge with respect to external electric field by magnitude of electric charge, then we get rid of it from the system, and then we consider only electric field, and that's when we introduce the concept of electrostatic potential, which is as well as potential energy, also a scalar quantity, and describes uniquely the properties and the distribution of some considered electric field. So what is the relationship between electric field vector and electrostatic potential? So in terms of units, we derive units for electric field, and we have shown that there was volts, which unit for electrostatic potential, per meter. So magnitude of electric field can be quantified in units volt per meter. So what does it tell us? So if we want to determine electric field magnitude from electrostatic potential distribution, then the magnitude of electric field is proportional to the rate of electrostatic potential change along certain distance, like a certain direction. So we consider how much electrostatic potential is changing per unit distance along given direction, and that gives us the magnitude of electric field in this given direction. So if we want to get it in vector form, we consider this as the end of the discussion last time. We need to take partial derivatives of electrostatic potential distribution, V as a function of x, y, z, and we take partial derivatives of this electrostatic potential distribution, so dv over dx, times I unit vector, that is component of electric field along axis x. Then we have next component, which will be dv over dy times j unit vector, that will be component of electric field vector along axis y, and the same for axis z, dv over z times k unit vector. So why we care about this? Because it is much easier to determine electrostatic potential distribution next to some continuum of electric charge in comparison to determining electric field vector. Because when we deal with electric field vector, we need to sum vectors of electric field in a given point, which are created by each small segment of this continuum of electric charges. So it is quite challenging to add vectors. However, electrostatic potential is a scalar quantity. And scalar quantity, we just add numerical values. So it's much easier to determine net electrostatic potential in a given point created by some continuum of electric charges. And then when we know electrostatic potential distribution at any point around this continuum of electric charges, we can take this information into account as this function B is a function of x, y, z in three-dimensional case. And by taking simple partial derivatives, which is a quite easy task, we can determine, based on this information of electrostatic potential distribution, determine electric field vector at any position. So that is the general approach, how we can use the relationship between electric field and electrostatic potential in order to determine quantitatively electrostatic, like electric field vector. So now we proceed further, and our topic for today will be capacitors. So any ideas, suggestions, what is that, and what we define under this word capacitor?
Capacitance is the ability of some material will save some amount of charges.
So I would say that in general definition, it's not ability of material, but like ability of an object to accumulate some electric charge on it. So we will show why this is about more like object, because actually geometric like capacitance of different conductors will be actually defined by their geometric size and shape. So that's why we are talking more about object properties, geometric properties, than properties of the material of which this object is made of. We assume that we have two conductors. Let's say they possess different in sign but equal in magnitude electric charges. So let's say we have one conductor. So this is Q plus. Then we have another conductor, Q minus. So obviously there will be some, we can draw these electric field lines which originate at positively charged object and terminate on the negatively charged object. And there will be some potential difference between these two conductors since they possess different charges. So they will be, their surfaces will possess different electrostatic potentials. So the amount of electric charge which can be accumulated by such system, which is a system of two conductors. Usually these conductors are called plates because most common capacitor is a parallel plate capacitor. So these conductors are usually called plates. And the ability of accumulating electric charge is defined by capacitance of this system. So we can write that total charge Q, which can be accumulated at this capacitor, will be proportional to the potential difference. And here is some proportionality coefficient, C. And this proportionality coefficient is actually called capacitance. So this is the feature of the system of two electrodes, two conductors, which defines how much charge can be accumulated by the system. So usually we can see in electrical circuits representation of a capacitor in this form when we have like two plates of a parallel plate capacitor depicted. Sometimes you can see such a sign with an arrow. That means that we have a capacitor with tunable capacitance. So we can change this capacitance within some ranges. So the units for capacitance, see, that is farad, which is coulomb per volt. So farad is quite large capacitance. 1 farad is actually huge capacitance. That's why we are going to operate with usually like micro or nanofarads. So what is micro and nanofarads? 10 to the power of what? Minus for nano minus nano. So there is nanometer also, and nano in this particular case nanofarad. So now let us consider what will be capacitance of a single conductor in a spherical form. So it's actually not so critical to have two plates. Can consider a single conductor, which also will have some ability to accumulate electric charge. So we can determine capacitance of a single conductor, and then when we go to two conductors, when we have two plates, that will be actually a classical capacitor, and we of course will consider this case too. So let us first start with a sphere with some radius a. There is some positive charge q residing on the surface of the sphere, and what we also, so obviously for this condition, the surface of the sphere will possess electrostatic potential, let's call it V1. So then let us consider electrostatic potential at a distance which is approaching to infinity. So here, let's say radius of this sphere, which surrounds, imaginary sphere, which surrounds the real electrically charged sphere, will approach to infinity. So here we will have some electrostatic potential V2. As you remember from previous discussion, it doesn't matter actually what is the magnitude of electrostatic potential, because we always can pick up a certain point which we assume to be a point with electrostatic potential equal to 0, and measure electrostatic potential of other points with respect to this 0 value. So that's why at this given example, we can consider that at distance from this charged sphere equal infinity, electrostatic potential will be equal to 0. So we define this V2 as 0 at r equal infinity. So we keep this in mind, and that's why the potential difference between infinity and surface of the electrically charged sphere will be equal just to V1. which is the electrostatic potential of the surface. So now what will be the electrostatic potential of the surface? V1, it will be equal to Q with electric constant Ke times Q, magnitude of electric charge, which is accumulated on the residing on the surface of this sphere, and divided by radius of the sphere. So this is electrostatic potential of the charged sphere. And now we can determine capacitance of such conductor, spherical conductor. So capacitance from this definition, we can write that it will be electric charge Q divided by potential difference between the surface of the sphere and some point at the infinity. So that will be electric charge Q divided by V1. And we will have Q over Ke, Q over A. So eventually we end up with A, which is radius of the sphere, divided by Ke. And recalling the equation for like definition of this electric constant, we have 1 over 4 pi times epsilon naught. We can write here that will be 4 pi epsilon naught times A. So that is the capacitance of spherical conductor. We have some constant here, 4 pi times epsilon naught, which is permittivity of free space, and times radius of this conductor. Who remembers what is the magnitude of this permittivity of free space?
8.87.
8.85 something, 10 to minus 12. And as you see, 10 to minus 12, that is very, very small number. So it's actually 3 orders of magnitude less than 10 to minus 9. So that's why even if radius of the conductor, of the spherical conductor is quite large, multiplying by this extremely small number will result in quite small capacitance. So that's why I mentioned that 1 farad is huge capacitance actually, and that usually the common values for capacitance are much smaller than 1 farad. So now let us switch from one conductor system and capacitance of an isolated conductor to actually a classical capacitor when we have 2 electrodes. So we will consider a parallel plate capacitor with 2 parallel plate electrodes. Yes.
So, according to the formula, capacitance depends only on the radius.
That's a good question, and I think we could have discussed it all together with parallel plate capacitor, but we can also mention it here. So as you see, the capacitance of this spherical conductor depends actually, is proportional only to the radius. So this is just a constant. So means that there is only geometrical feature which defines the properties of this conductor. It makes a difference for the magnitude of capacitance and ability of the conductor to accumulate electric charge. Its capacitance does not depend on charge, so it doesn't matter how much charge we have already accumulated at the conductor. Its capacitance will be the same regardless on the magnitude of electric charge previously accumulated. So it doesn't make a difference either you start charging electrically neutral conductor or you charge some conductor which already possesses certain electric charge. Capacitance of this conductor will be defined only by geometrical features of the electrode. And we will show that for capacitors, for parallel plate capacitor, we actually get similar dependence. We will see that capacitance of a parallel plate capacitor will be also defined exclusively by geometrical features of this capacitor. So let us consider two parallel plates which carry equal in magnitude but opposite in sign electric charges. So we have plus Q and minus Q. Who will remind me the expression for electric field next to infinitely large surface, like charged surface? We had some expression for this electric field magnitude, which is related to the surface density of electric charge residing on the parallel plate, such a plate. So that was electric field sigma to epsilon naught. So we don't have area there, so it's like independent on area. So it was cancelled out in the derivation. So we got that from application of Gauss law for the case when we have infinitely large surface with uniform surface density of electric charge sigma. So this is the magnitude of electric field, and this electric field vector is oriented perpendicular to the surface. So we can draw here, maybe let me change the color so it will become clear to you. So that's positive, let's use red. Please pay attention here so you understand once and forever the simple explanation of parallel plate capacity. So this will be electric field vector created by left plate of the parallel plate capacitor, oriented perpendicular to the surface of this plate, and it goes from the plate because the plate carries positive electric charge. So that's how it looks here. And obviously it will go also in the opposite direction, so inside the space between two plates. So we can write it here also, like this, draw. So now let us consider negatively charged plate. Here, how the electric field vector will be oriented? Towards the plate. So we can draw, how better we will do this, let's say like this. From this side we have electric field vector. Then we have here. So I just show two vectors here, doesn't matter. And obviously we have from the internal side of the capacitor, like for instance, space between two plates, we have electric field vectors oriented like this. So keep in mind that the magnitude of these vectors are the same. They are equal to this expression, like sigma divided by 2 epsilon naught. Sigmas are the magnitudes of surface charge density. They are the same for two plates because area of the plates is the same and they carry the same electric charges in magnitude. So now what do we see? That here magnitude of electric field is equal to sigma divided by 2 epsilon naught. The same will be here. However, inside these two vectors, they coincide in the direction. So means that electric field created by positively charged plate of the capacitor and negatively charged plate of the capacitor, they enhance each other, and we have twice larger electric field inside this configuration than outside. Does it make sense? Okay, so that's why electric field inside a parallel plate capacitor will be equal to sigma divided by epsilon naught. So it's uniform electric field. However, it is twice larger inside than outside. So now, when we have expression for the electric field, uniform electric field inside the parallel plate capacitor, by the way, we can express it also as Q, magnitude of electric charge accumulated by this capacitor, divided by epsilon naught, and A, which is area of these plates of the capacitor. So now let us determine what will be the potential difference between these two electrodes. Any suggestions?
Quite by distance between
Electric field magnitude multiplied by the thickness of the capacitor or distance between parallel plates. So this we can define as some distance d, and potential difference between two plates will be electric field, uniform electric field inside the capacitor times this distance d. So now we can substitute here the expression for electric field inside, and we get Q times D divided by epsilon naught times A. So now we finally come to the definition of the capacitance of such parallel plate capacitor, C. And as you remember, we defined it earlier. It's Q, electric charge, divided by delta V, difference in potential, electrostatic potential. So here it will be Q divided by Q times D over epsilon naught times A. And we end up with epsilon naught times A divided by D. So this is the expression for capacitance of a parallel plate capacitor. And please keep in your memory not only the expression, because that's kind of important. It's comparable to Ohm's law. You need to know this. And ideally would be to remember also this explanation where it's a very fundamental part of electrostatics. So as you see from this equation, we have some constant in numerator, then we have area of the plates, we can call it area of the paraplate capacitor, and d, which is the distance between the plates. So we don't have any other parameters. For instance, electric charge is also cancelled as in the previous example, and here are only geometric features of the system of two electrodes, two conductors, which are considered in this given case as parallel plate capacitors when we have just two plates. So we have area proportional to area and inversely proportional to distance between the electrodes of the capacitor. So now let us proceed further and consider accumulation of no, not accumulation of energy in capacitors. That will be next step. We need to consider connection of capacitors in parallel or in series. So as I mentioned earlier, we have an option to graphically represent a capacitor with this sign. So let us assume that we have a parallel connection of two capacitors. So we have a capacitor with capacitance C1 and C2. So here is plus and minus. Some battery is attached to this system of two capacitors. And here will be some potential difference between electrodes, delta V. So potential difference over capacitor C1 and capacitor C2 will be the same or different? The same, because they are connected in parallel, so their potential should be equal. So we can write that delta V is equal to delta V1, and that is equal to delta V2. Now we understand that there is some electric charge accumulated at the plates of these capacitors. So total electric charge will be equal to electric charge accumulated at first capacitor plus electric charge accumulated at second capacitor. So now we want to determine some equivalent capacitance of these two capacitors connected in parallel. And in order to do that, we can express these charges in terms of capacitance and potential difference. So we know potential difference, we know what potential difference we apply to this system is delta V, and we can write that C equivalent capacitance of these two capacitors connected in parallel times delta V potential difference will be equal to C1 times delta V plus C2 times delta V. So we can cancel out this potential difference because they are equal for all cases. And eventually we see that equivalent capacitance of such a battery of capacitors connected in parallel will be C1 plus C2. So that is the way how we determine equivalent capacitance of capacitors connected in parallel. We just sum up their capacitances. And that is because the total charge will be equal to sum of total charges and electrostatic potential difference between electrodes of these capacitors will be the same. So now another option of connecting capacitors, we can go for series connection. So this will be capacitor 1, capacitor 2, connect to the battery. So keep in mind here that initially both capacitors are not charged, so they don't have any charges. Then we connect them to a battery, plus minus, so we have plus, minus, and then here minus, here plus. So the potential difference between terminals of this battery will be delta V. And now we need to also determine potential difference between capacitors, like plates of the capacitors. So this will be delta V1, and here we will have delta V2. Can we write here as in previous case that delta V is equal to delta V1 and delta V2? No, because they are connected in series, so we need to write that delta V is equal to delta V1 plus delta V2. So this we keep in mind. However, we can write something interesting about electric charge accumulated in these capacitors. So as you remember, initially this system was not charged. We didn't have any charges there. So we attach it to a battery and charge both capacitors. Plates are charged with opposite signs but equal magnitude, and as a total system it remains electrically neutral because all these charges compensate each other. So now this electrode of capacitor 2 is connected to the terminal of the battery. This electrode of capacitor 1 is also connected to the terminal of the battery. So that's where we provide charges from battery to these electrodes of the capacitors. However, these internal electrodes, as we show it here on the figure, and this wire which connects them, they are totally isolated from the battery. So there is no connection between battery terminals and this conductor. It's actually one conductor because this is one conducting plate, this is another conducting plate, and it's connected with a wire. So here we have insulator, like air, and here insulator. So it's not connected to the terminals of the battery. Now, if this conductor was electrically neutral before we connected the battery, it should remain electrically neutral after we connected the battery because we didn't connect the battery to this conductor. So it was connected only here and here. So we have positive and negative charges here, so they should be equal to each other in magnitude and opposite in size. So this conductor by itself should be electrically neutral as before connecting to the terminals of the battery. So that means that charge here accumulated, positive charge, the magnitude, is equal to magnitude of this negative charge here. Means that the charges which are accumulated by capacitor C1 and C2 are equal to each other. So we have Q1 is equal to Q2. Oops. So we are talking about magnitudes. And we can express it with just some charge Q. So now we have different potential difference between electrodes of the capacitors, but electric charges which are accumulated on each of capacitors connected in series, they are equal. So now we can express potential difference in terms of capacitance. So how we do that? Potential difference is equal to charge Q divided by C, capacitance. So we can write that this is equal to Q over C1 plus Q over C2. And here it will be some equivalent capacitance of these two capacitors connected in series. Since these charges are the same, we cancel them out, and we end up with 1 over C equivalent equal to 1 over C1 plus 1 over C2. So this is the way how we determine the equivalent capacitance of two capacitors connected in series. And what it means here that the equivalent capacitance will be smaller than the smallest of these two capacitors. If we connect them in parallel, we just add up, then obviously equivalent capacitance will be larger, will be equal to sum of capacitances. However, if we want to get, if we have two capacitors and want to get a smaller capacitance equivalent, so obviously we need to connect them in series, and that will allow us to get a smaller capacitance as of the battery of capacitors. Obviously, if you have more capacitors connected in series or in parallel, you just add here more terms to this equation. Okay, guys, so let us summarize our discussion for today. We introduced the concept of accumulating, like ability of conductors to accumulate electric charge that is quantified by such parameter as capacitance. So a single isolated conductor possesses certain capacitance, it can accumulate charges. So we have shown on the example of a spherical capacitor how we can determine its capacitance and quantify its ability to accumulate charges. So capacitance is used as a proportionality coefficient between accumulated charge and potential difference. So accumulated charge can be expressed as capacitance times potential difference. And the most common example of a capacitor is parallel plate capacitor, which we considered in details and derive equation for the capacitance of such a parallel plate capacitor. Assuming the uniform electric field inside the capacitor in between two electrodes and distance and area between these electrodes. So we also consider possibilities to connect capacitors in series and parallel. So for parallel connection of capacitors, the equivalent capacitance increases, actually defined as sum of capacitance of each capacitor connected in parallel within this battery. And when we connect capacitors in series, the net equivalent capacitance of the battery will be smaller than the smallest capacitance of the capacitors connected in series. So we will continue next time from the energy accumulated in a capacitor and proceed further with electric current. So thank you very much for your attention. See you next time and have a good evening. Bye.